All right. So, Monday, I was gone. Did you guys watch the video?
Yeah.
Yeah. It was largely a review of things you did last year,
I
right?
heard some coughs in there.
It was a video from last year, so if it was, I was also sick at the same time last year.
It must have been coming from Mr. Ryan.
Yeah.
It was the same time last year.
You guys
This is about the time of Mr. Ryan.
you guys worked on worksheet 1 afterwards, right?
Yeah, worksheet 1.
Any questions on that? Was that okay?
That was pretty swell.
Pretty swell.
Just a nice little overview.
Okay. Fair enough then. Today, then we're going to be starting in with chapter 5. Oops.
Mr. Ember came behind it.
Okay. I put it in her box, but okay, dokie. What else? Honors Trig, chapter 4. That's you. You should be good. You're welcome, Tommy. Sorry about that. Nanook of the North. I think we might be a little overdressed here.
No.
It's okay.
No hood down in the hood.
I mean, it's a reasonably temperature in this room, right?
It's literally drenched.
It hasn't been dried yet. Made it
All
to
right.
the washer, never made it to the dryer.
Yeah, and she just took it right out of the wash. So no.
That's actually like 40.
Alright, let's
Please. Please.
No.
All right. So, today, chapter 5, section 1, we're going to be talking about trigonometric identities. So some of these identities are things that we've already kind of inherently talked about that we're just going to formalize. Some of them are going to be maybe kind of new-ish, and then we'll talk about like how we can kind of use these to do some problems, okay? So when we talk about an identity, when I say an identity, what I mean is just like an equality statement. That's valid for the given variable. So like a super trivial example of an identity, say we have the statement 2x plus 6. I know that I can take like a greatest common factor of 2 out of that. So the statement 2x plus 6 equals 2 times the quantity x plus 3. This is an example of an identity. Now it's a trivial identity, but like that's true for all values of x. So moving on into trigonometry, our first set of identities are called the reciprocal identities. And these are not where I had you before. Let me Stupid thing. Now, these are things that we had already kind of talked about before. So, for example, that cosecant is the reciprocal of sine, secant the reciprocal of cosine, cotangent the reciprocal of tangent, and then so on and so forth, right? These are all things we kind of talked about way back in like chapter 2. But we're going to rewrite now formally and call them an identity. Our next set of identities, and just FYI here, guys, all these identities that I'm like dropping in, I've already collected together for you on this sheet. So don't feel like, they're already on this basic trig identity sheet in the OneNote. Just FYI. Our next set of identities, remember the unit circle, right? How do we calculate tangent on the unit circle? Y over x. And y on the unit circle is the same as sine, and x is cosine. So I could say that tangent is sine over cosine. That's going to be our next set of identities. We call these the quotient identities. That tangent is sine over cosine, and then cotangent, which is the reciprocal of tangent, should be then cosine over sine. We okay there? All right. To get our next set of identities, let's imagine that we have this right triangle here. And we'll say that this angle here is my theta. Relative to theta, this side is the adjacent side. This side is the opposite side. And that side is the hypotenuse. Everybody cool with that? So if I use SOHCAHTOA, I can say, for example, sine theta is opposite over hypotenuse, or that cosine theta is adjacent over hypotenuse. Everybody's okay with that? So let's consider then what sine squared theta plus cosine squared theta equals. Everybody's cool? Well, we said that sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So sine squared plus cosine squared has to be opposite over hypotenuse squared plus adjacent over hypotenuse squared. Is everybody okay with that idea? And then how do I square a fraction like that? Good, we square the numerator and we square the denominator. Everybody's cool with that? What do you notice about those two fractions? They have a common denominator, so let's write them as a single fraction. What's opposite squared plus adjacent squared have to equal? Why? Olivia? Yeah. Remember, these are the legs of a right triangle. So a squared plus b squared has to equal c squared. In this case, that is hypotenuse. And what's hypotenuse squared over hypotenuse squared? 1. So if I take this together, I can say that sine squared theta plus cosine squared theta is equal to 1. Okay? If I start with this identity now, let's see what happens if I divide both sides of the equation by sine squared theta. What's sine squared theta divided by sine squared theta got to be? Sine squared divided by sine squared? What's that? 1. What's cosine squared theta divided by sine squared theta have to be? Well, let's go back to here. I know cosine over sine is cotangent, so cosine squared over sine squared should be cotangent squared. Great. And what's 1 over sine squared have to be then? Cosecant squared. Excellent. Yeah, so if I go back to here, I notice that 1 over sine is cosecant, so 1 over sine squared is cosecant squared. This will also become an identity. What if we start with that sine squared plus cosine squared is equal to 1, but this time instead of dividing everything by sine squared, I divide everything by cosine squared. What's sine squared theta divided by cosine squared theta got to be? Well, let's go back and check. Sine over cosine was tangent, so sine squared over cosine squared is going to be tangent squared. And cosine squared theta over cosine squared theta is 1. And 1 over cosine squared is secant squared. That's also going to be an identity. We're going to package those 3 guys together, and we're going to call those group of 3 the Pythagorean identities. God bless you. For our next set of identities, I want to point out the following observation. So we've been using the unit circle for a while now, right?
Yes.
If you notice something like, if I look at the unit circle and I look at sine of 30, I get 1/2. If I look at cosine of 60, I also get 1/2. And if I look at sine of 60, I get square root 3/2. And if I look at cosine of 30, I get the square root of 3/2. What do you notice about the angles in this situation? Okay, well, what if I did sine of 45 and I look at cosine of 45? What do I notice about the angles in these situations? They add up to 90 degrees. Well, there's a word for that. Do you remember what that word is? Starts with C. It's a geometry word. Yeah, those are complementary. So have you noticed we have sine, right? And then we have cosine. You know, have you ever wondered what the co is short for? Complementary. Yeah, these are what are called complementary functions because sine of theta equals cosine of the complement of theta. Now, symbolically, how do we say the complement of theta? That'd be 90 minus theta. But when we do trigonometry, do we use degrees most of the time or do we do radians most of the time? Radians. What's 90 degrees in radians? Pi over 2. So we have that identity. And we can do that for every co-pair. So sine and cosine, this relationship holds. Cosecant and secant, this relationship holds. Tangent and cotangent, this relationship holds. So when we go and we build that out, we end up with the 6 co-function identities. Uh-oh. Uh-oh. Did I just delete that? There, it's back. Guys, Control Z is your friend.
Pi over 2 minus theta.
Correct. That's just symbols for the complement of theta, right? All right. One more set of identities, and then we'll start looking at some problems. So remember way back in chapter 1 when we talked about odd and even functions? You remember that name anyways?
Yeah.
we said odd functions had this property, that f of negative x is equal to negative f of x. Even functions have this property, f of negative x equals f of x. Remember that?
Yes.
And remember in chapter 3 when we talked about the graphs for sine, cosine, and tangent, we identified that sine and tangent were odd functions and cosine was an even function. And since sine and tangent were odd, their reciprocal functions, cosecant and cotangent also have to be odd. Oh boy. And the reciprocal function for cosine, secant, has to be even. So if I take these two ideas, that sine is an odd function, I can say like sine of negative x equals negative sine of x. Or since cosine is even, I can say cosine of negative x equals cosine of x. And I can do that for each of the trigonometric functions based on just whether they were odd or even. And that gives me the set of identities that we'll call the odd-even identities. So for the most part, these identities that we saw today were all things that we kind of knew already. We've just kind of formalized them together or connected some dots of track that we've already laid in previous chapters to come up with these things, right? We didn't do anything exceptionally sneaky here. Bless you. Okay, so let's look at some examples then. So here it says find sine theta if tangent of theta is equal to 3 and cosine of theta is equal to, or is negative, So this was something that we did way back in chapter 2. Let's just kind of review how we did that back in chapter 2. Here we see that cosine is negative. What quadrants does theta have to be in for cosine to be negative? Two and 3, right? Cosine is negative where the x-coordinate is negative. And here we're told tangent is 3, and 3 is a positive number. So what quadrants does tangent have to be positive in? 1 and 3, because we need both the x and y's to have the same sign, because tangent is y over x. Okay, so if I do that, and I draw my picture, let's use different colors here. I'll draw my standard position angle. So that's like my theta there, right? Now, if I use my point on the terminal side of a standard position angle definition for sine and cosine, I have some point x and y, and then I have some distance from that point to the origin, r. If tangent is y over x, and I know tangent is 3, I know y over x is 3. So if I think about that as just 3 over 1, I can say that y is 3 and x is 1. Everybody's okay with that? But what quadrant are we in? 3. So what should I really write here? -1 and -3. And then how do we find that r? R is the distance from the origin to that point. So how do I calculate r? Just using the distance formula, right? But since the origin is 0, 0, I have like the square root of x minus 0 squared plus y minus 0 squared. And like x minus 0 is just x and y minus 0 is just 0. So I have this. So we get the square root of 10 is the length for r. Everybody's cool with that? Okay. And if I use that point on the terminal side of a standard position angle definition, I know sine is y over r. So I have everything I need. To get sine. Everybody okay with that? You guys vaguely remember doing that? It was a long time ago, but we did that. We can accomplish this same thing using only identities. Let me just steal this again real quick. That was, anyways, I don't care that it deleted half of my method too. You guys are cool with it, right? All right. So what I'm going to do is I'm going to first start by looking for an identity that involves only tangent and only cosine. So if I go back and I look at my identities, looking for something that involves only tangent and cosine, I don't see one. But I see something that's close. I see this. Why is that close? What is secant the same as? 1 over cosine. Yes, sir. Sure. So I'm going to use this one because that involves tangent, what I know, and then kind of cosine, which is the other piece I know something about. So I know tangent is 3. And I know secant squared is 1 over cosine squared. So I know 10 is equal to 1 over cosine squared. If I do the reciprocal of both sides, I get that cosine is 1 over 10. Or cosine squared is 1 over 10. We'll do the square root of both sides. Now, when I do the square root of both sides, what do I have to remember? Plus or minus. Now, the square root of 1 is just 1. So I'm just going to write that as plus or minus 1 over the square root of 10. But what was I given about cosine in my problem? So what does that tell me about the plus or minus? It's just minus. Very good. Okay. So now that I have this, what I'm going to do is I'm going to look for an identity that involves sine, tangent, and cosine. Do you guys see an identity there? I do. The quotient identity that says tangent theta is sine theta over cosine theta. So to get the sine theta by itself, that's what we're looking for. I multiply both sides by cosine theta. And I know cosine theta is negative 1 over square root of 10. And I know tan theta is 3. If I multiply those together, I get negative 3 over the square root of 10, which is the same thing that we got using the previous method, right? What was the advantage of using the identities? Well, there's no picture I had to draw, right? There's nowhere where like, oh yeah, I have to remember because it's in the third quadrant, I had to make things negative. It just using identities, right? What's the difficult part about this? Figuring out which identity you need to use, right? Will that be something, is that going to be something that's going to get easier as you go? Yeah, it should. So the other type of problem that you're going to be asked to do in your in the homework is going to be simplifying a expression involving these trig functions. So when we ask you to do a simplifying problem like this, there's kind of two sets of tools that you can use. Two sets of things you can do. First thing you can use, you can do algebra stuff. So factoring, foiling, adding fractions, combining like terms, things like that. That's all fair game. The second thing you can use are identities to take like two things and turn it into one thing. Everybody's okay with that? Typically, what you'd want to do is you'd want to start by looking for algebra stuff to do. And after you've done your algebra stuff, then you probably start looking at identities. Does it have to be that way every time? No, but you guys are still trying to build out some intuition of like how to do these problems. That's a good starting place, is to just every time start by looking for algebra stuff before going to your identities. All right, so let's take a look at this example. We have sine cubed plus sine x times cosine squared x. Does anybody see an algebra thing I can do there? Factoring, foiling, combining like terms, adding common denominator, or making a common denominator, adding fractions. Anything like that you can do here. There are no like terms to add here. Nope, there's something to do here. What is it, Emma? So how many terms do you have here? There are 2 terms, right? Remember, terms are things that are being added or subtracted. So I have this term and this term. Everybody agree with that? Do you notice anything in common between those 2 terms? There's a sine x in common with both of them, right? So let's factor a sine x off. When I do that, sine cubed x becomes sine squared x. And sine x times cosine squared x becomes cosine squared x. Everybody okay with that? Like the easiest kind of factoring that you remember, not quadratic factoring, just like a greatest common factor thing. All right. So we did some algebra thing. Notice what happened here. We took something that had 2 terms and turned it into one thing, one multiplication problem, right? That's usually better when it comes to simplifying. Do you guys see any identity things that we could use here? I do. Take a look. See if you can find something. Yeah. What does sine squared plus cosine squared equal? Mm-hmm. Actually, I'll just write it this way. And what's sine x times 1? And are we going to be able to do simpler than just one thing? No way, man. That was kind of fun, right? Look at that. We took that complicated expression and showed that it was just really just sine x. That's pretty neat. Let's do another. So let's say we want to simplify the expression secant x minus 1 times secant x plus 1 all over sine squared x. Typically, we start by looking for an algebra thing to do. Does anybody see any algebra thing to do, like factoring, foiling, common denominator, combining like term? Emma says foil, which I think is a great idea, right? It's staring right at you. That looks like a foil problem right there. Notice that what kind of foil problem is that? It's a difference of 2 squares set up. So I can FOIL this out just like quickly in my head, right? Just to be a squared minus b squared. Everybody happy with what we've done so far? Okay. What do we typically do next? Look for an identity, right? Take a moment, take a look, see if you see a good identity going on there. I see one. This one's a little bit more subtle. Let me give you a hint. Notice in this problem we have a secant squared and a sine squared. What identities involve squareds? The Pythagorean ones did. That's probably where I would start my look or my search at. What is secant squared x equal to? One plus tangent squared. Now, why is that going to be effective for me? That seems like I just traded one thing for two. That seems like a bad idea, Mr. Kulik. Yeah, so the plus one here and the minus one add to give me 0. So that's actually a great thing, right? We just now have a single numerator, tan squared, and a single denominator, sine squared. Now, let me give you a little helpful hint when you get to a step like this. It's probably going to be more effective to think about it this way, as tan squared times 1 over sine squared. Well, why, Mr. Kulik? That seems like you're making it worse. Well, what is tan squared? Well, tangent is sine over cosine. So tan squared can be sine squared over cosine squared. And look at what happens. What can happen when I have these two fractions? The sine squareds cancel out, and I'm left with not cosine squared, 1 over cosine squared. And that is the same as secant squared. Yes. Now, are these going to get easier as you do them and get more practice? They should, yes. Are they going to feel pretty hard in the beginning? Yeah. The reason they're going to feel hard is that there's not like one set way to do them over and over and over again. It's not like they're all going to be done exactly the same way. You're going to have to develop a little bit of intuition to kind of see what to do. And when you're first starting this, you have no intuition because you haven't done any of these problems and you're not like, haven't seen any of the patterns, right? When we're doing this, I'm going to try to point that stuff out to you and talk about like, usually the first thing you want to do is an algebra thing. And like, when you see something like this, I start looking at these identities first. And like, I'm going to try to spoon feed you that stuff. But at the end of the day, it just comes down to like, you have to spend some time kind of grinding on this stuff. You know what I mean? Like figuring out stuff that works and doesn't work. And all right. Let's look at the next example. What do we usually start by looking for? Algebra thing. Any algebra thing you see in particular that you'd like to do? Well, I certainly think there is something.
Yeah.
Yeah, Emma says common denominator. I have two fractions that are being added or subtracted. In order to do that, I'm going to need a common denominator at some point. So let's do that here straight away. What would the common denominator be between 1 minus sine x and cos x? What would the common denominator be of like 2 and 3? 6, which is 2 times 3, right?
Yeah.
So the common denominator here would be 1 minus sine x times cosine x. Those two things are relatively prime. They have nothing in common. So the least common multiple, the thing that would make our common denominator, is just going to be the product of those two things. So that first fraction I'm going to multiply by cosine over cosine. And the second fraction will multiply by 1 minus sine x over 1 minus sine x. Everybody okay with that? All right. Cosine times cosine is cosine squared x. Negative sine x times 1 is negative sine x. Negative sine x times negative sine x is positive sine squared x. And the denominator here, I'm going to just leave. Sure. I'm just going to leave the denominator in a factored form. Why? Why would Mr. Kulik do that? Why not multiply the denominator out? What's the goal in this problem? What are we trying to do? Simplify. In order to simplify, at some point I'm going to want to reduce the fraction, correct? To reduce a fraction, it must be written in a factored form. Now the numerator I multiplied out because I have subtraction going on there, right? Until I do that subtraction, I'm not going to be able to factor. That's why I multiplied the numerator out. But the denominator is already in a factored form. I'm not going to multiply it out just to factor back later on. I'm just going to leave the denominator the way it is. Everybody cool with that reasoning? In general, on a simplifying problem, that's what I would always do when I'm making a common denominator, is I don't multiply the denominator out. Unless I see some good reason to do so. Okay. So we made a common denominator. What do you want to do next? Is there any more algebraic things to do? The only thing you'd have left is like a common or a like term to combine up top, which we don't. So it's probably identity time. There's a good one that jumps right out at me. I'm going to give you a minute and let you think on it so that like we can start building some of this intuition that I've been talking about. I have a sine squared and a cosine squared. Can those be added together? They're not written next to each other. Is it okay to just add those two together? Yeah, I just have three things that are being added. Doesn't matter the order that I do that. So what is sine squared and cosine squared? Or sine squared plus cosine squared? 1. And then I still have that minus sine squared up there. Okay. What can I do now? Factor. So I cancel like this? No. Cannot cancel part of an addition or subtraction problem, but I can cancel the entire 1 minus sine x. I want to be clear. So what do I get when I do that? 1 over cosine x, which is secant. Very good. Notice that if I would have multiplied out the denominator to do that reducing step we just did, I would have had to factor it back out again, which, like, why am I doing it twice? Is everybody okay on that one? Okay. I think I got one more here in my example list. Oops. Oops. I had two more. Okay. So simplify the expression sine x times cosecant negative x. Anything algebraic that I can do here? No, man, I just have two things that are being multiplied together. I mean, there's nothing really I can do with that. What identity would you want to use here? Yeah, I want to get that, use that odd-even identity. I need to get the variables the same. One of them's an x, one of them's a negative x. So I'm going to use the odd-even identity that says cosecant of negative x is negative cosecant of x. Be okay there? Or really the same thing as negative sine x times cosecant x. What can I do with that? What's cosecant? It's 1 over sine. Yeah, so I'm going to think about this as sine x over 1 times 1 over sine x. So what can I do there? And I'm left with just, well, negative 1. Remember, we had this negative sign over here. And we're done. Certainly can't get simpler than negative 1. All right. Now I'm on my last one. I missed this little quickie in there. All right. So for something like this, before I even start looking for algebraic things, there's an identity that I would use first. Yeah, I would use a function identity so that my variables are all the same. I want them all to be y's. So what can I say here? We can do that. Everybody happy there? Okay. Any algebraic thing you can see to do here? You could distribute the sign through if you wanted to. I'd probably wait to do that. I don't see any big advantage of doing that straight away, so I would just hold off on it. So it's going to become identity time. Any obvious identity that you guys see to use? When the answer to that question is kind of no, like the Pythagoreans are all out because there's no squared things in here. You know, like the only thing you really have to work with are the reciprocal and quotient identities. Here's what I would say. In this sort of situation, I would try to rewrite everything in terms of sine and cosine. So I'm going to use the quotient identities to rewrite cotangent as cosine over sine and tangent as sine over cosine. And now that I have these fractions, what do you think I should be doing? I can't reduce because it's not a multiplication symbol, but I can make a common denominator. What would the common denominator be between these two fractions? Sine y times cosine y. So the first fraction I'm going to multiply by cosine y over cosine y. And the second one by sine y over sine y. So I'm going to have cosine squared y plus sine squared y. Oh, I like that. Over sine y times cosine y. What do you guys notice now? Cosine squared plus sine squared is 1. And what else do you notice? I can think about that as sine over 1. So those guys can reduce down. So what am I left with now? 1 over cosine y, which is just secant y. All right. Cool beans, daddy-os. So what I'd like for you guys to work on is 1 through 14. that feel okay to you guys? Yeah, I guess. All right. Stop.